Hello. We are going to talk about bond energies. So if you remember back in chapter 5 with thermochem, there were like 7 different ways to calculate the heat transferred in a chemical reaction, or delta H. And we said that we're going to skip bond energies for now because we had not learned how to draw Lewis dot structures yet. We haven't reviewed them yet. And we need to be able to see the bonds in order to calculate delta H of a reaction using bond energies. So bond energies, or bond enthalpies, are how much energy is transferred when you break or form a bond. Remember that when you have a chemical reaction, you take your you take your reactants and form products. And so you need to take the reactant particles or molecules and break those bonds. And when you break a bond, you have to put in energy. Think of it as like a pencil that you're trying to break. So you have to put in energy in order to do that. And so when you break bonds in the reactants, you have to put in energy, and so that is endothermic. And energy is absorbed by your system. Now when you form the products, you are forming the bonds in the products, and so forming bonds is exothermic. That means energy is released when you form bonds. That's because those particles are attracted to each other, so when you put them close together and form a bond between them, that's favorable and lower in energy, and so it releases that difference in energy. So breaking bonds is endo. So you're like you use positive enthalpies. Forming bonds is exo. So what you do in a chemical reaction is you're breaking and forming a bunch of bonds. So to calculate the delta H of the reaction, you just add up all the bond energies that you have in that reaction. Just keep in mind that if it's in the reactants and you're breaking those bonds, you use positive values because the energy is absorbed. And when you form bonds, like in the products, it's exo, so you use the negative values because the energy is released. And then the net would be your delta H of the reaction. These bond energies, or enthalpies, are listed for you at the very back of your packet, the very last page. There they are, and they're in kilojoules per mole. And again, these numbers you use either positive or negative depending on if you're breaking the bond or forming the bond. So if I'm making a CH bond, then my system would absorb 413 kilojoules per mole. If I'm forming this bond, then I would release 413, so negative 413 kilojoules per mole. So use these values, but be aware whether it's negative or positive. Something to note is that if you have like a double or a triple bond, the values are not the same as a single bond. So for example, a CC single bond is 348 kilojoules per mole, but a CC double bond is 614, and a CC triple bond is 839 kilojoules per mole. So watch out whether your bond that you're breaking or forming is a single, double, or triple. So let's go back to here and try a problem. So we have nitrogen reacting with hydrogen to form hydrazine. Hydrazine is actually like jet fuel. So if they are simple molecules like H2, you can probably imagine that in your head and use it without drawing them, but I highly recommend you draw them, especially for something like hydrazine or something like nitrogen. You know, when you look at this, you might not remember what it exactly looks like, and so I highly recommend that you just draw your bonds. So N2 looks like this. If you were just thinking, oh, N2 is just a single bond, you would get it wrong, right? So draw them out. It's a triple bond in between them, and the reason for that is because nitrogen has 5 valence electrons. So if you have 2 of those, you bond one set, and now each of them have 6. They need more, so bond another set. Now each of them have 7. Bond another set. Now each have 8. So that's the correct structure. And then I have NH2, it just looks like this, but I have 2 of them. If you want to just write a 2 here, that's great. I prefer to just draw 2 of them. That way I visually see that there's 2 of them. And then hydrazine looks like this. It doesn't matter where you put your lone pair and where you put your hydrogens, but each of the nitrogens has a lone pair, 2 hydrogens singly bonded, and then it's singly bonded to the other nitrogen. So then what you do is you say delta H of the reaction is equal to the sum of the bonds broken plus the sum of the bonds formed. You just need to remember that if it is in your reactants, that means we're breaking those bonds, and so you have to put in energy, so you got to use the positive values here. If you are forming these bonds, because they're in your products, that releases energy, and you use the negative values there. So delta H of the reaction is equal to, it doesn't matter where you start, I'll just start here. So we have, actually I guess I don't need those brackets there, I can just use regular parentheses. So we have 1 mole of the NN triple bond. Right, we're doing bonds. So the NN triple bond, if you look at the table at the back of your packet, it is 946 kilojoules per mole. My values might be slightly different. I think I updated your table in the back there. Sure. So I like to also kind of like scribble out the one that I did. So I did that one, so I know that I got it. Next I have HH single bond, and I have 2 of those. So 2 moles of HH. And remember, we're using the positive values here because they are being broken. 436 kilojoules per mole. So I got that one, got that one. Okay, got everything here. Let's look at the products. I have an NH single bond, and there's 1, 2, 3, 4 of those. So 4 moles of NH single bonds. And because these are in the products, they're being formed, so they're releasing energy. I have to use the negative, 389 kilojoules per mole. So I got this one, this one, this one, and this one. And now I just have 1 mole of N single bond N. And again, it's being formed, so I have to use the negative value, 159 kilojoules per mole. Again, if my values are slightly different from yours, it doesn't really matter. So all together, you just punch it in, delta H of the reaction is equal to positive 86 kilojoules per mole of reaction. And that's my answer. So overall, it is positive, which means the bond enthalpies of the reactants are more than those of the products, right? Because the products are negative, the reactants are positive, and we end up with a net positive. Be careful when you're calculating bond energies. A lot of people confuse bond energies with heats of formation. So on the side here, when you're using heats of formation, you do delta H of the reaction is equal to the heats of formation of products minus the heats of formation of reactants. Products minus reactants when it comes to heats of formation. When it comes to bond energies, you add all of them up. It's just you have to be careful to use positive values for the bonds broken and negative for the bonds formed. So they give you different results. So make sure that you are using the correct equation. Okay, let's do one more. Actually, a couple more. So this one says, using bond energies, calculate delta H for this reaction right here. So I highly recommend you draw out your substances. There's CH4. Then we have 2 Cl2s. And if you don't want to put your lone pairs, as long as they're not central atom, it's okay. You need lone pairs, obviously, if they're asking you for the structure, but if it's just for your work, it's not a big deal. And then we have two F2s. Then we have CF2Cl2. So we know carbon should be in the middle. We have 2 fluorines and 2 chlorines. It doesn't matter where you put them. Then we have 2 HF, so an HF and another HF. And then 2 HCl, so an HCl and another HCl. Okay, so we are going to say delta H of the reaction is equal to the sum of the bonds broken plus the sum of the bonds formed. We need to remember that the ones that are broken, those require energy, so we're going to use positive values. The ones that are formed, those release energy, so we're going to use negative values. So let's start here. We have 4 moles of CH single bonds, and the value for that is 413 or 414. Again, I think I'm using it in an old table, so your values should be close, but might not be exactly the same. So that takes care of this one, this one, this one, and that one. Next, I have 2 Cl-Cl bonds. And positive value again, 246 kilojoules per mole. Took care of this one and this one. Next, I have 2 FF single bonds. And again, you use positive value, 159 kilojoules per mole. Okay, now to the products. We have 2 CCl bonds right here. In the products, so we need to make sure that we use the negative value. And the CCl is negative 330 kilojoules per mole. So we did this one and this one. Next we have 2 CF bonds being formed, so negative value. CF is 439 kilojoules per mole. We got this one and this one. Next we have 2 HFs. HF single bonds formed, so negative value, 569 kilojoules per mole. So we got these two. And then finally we have 2 HCl single bonds, negative value because they're formed, 461 kilojoules per mole. And you add them all together. At the end, you get negative 1,172 kilojoules per mole of reaction. When we say per mole of reaction, remember that means for the reaction is written. So for 1 mole of methane, 2 moles of chlorine, 2 moles of fluorine, and so on. All right, let's try this last one here. It says, using the following information, that the heat of formation of HCl is negative 92.3 kilojoules per mole. The bond enthalpies of the HH and the ClCl are 436 kilojoules per mole and 242 kilojoules per mole. Calculate the bond energy of the HCl bond in hydrogen chloride. So let's take a minute here. They're telling us some bond enthalpies, right? They're also telling us a heat of formation. So it looks like we're forming HCl. Let's write the formation equation for HCl. So HCl is formed from H2 and Cl2. And to balance it, we can't put a 2 here because heats of formation means it's forming 1 mole. So we have to balance it by putting halves here. So I'm going to write it out as Lewis dot structures here. All right, now this heat of formation means the heat of this reaction, right? So delta H for this reaction is negative 92.3 kilojoules per mole. This is the reaction of formation of the HCl. So that's what that means. they are giving us the bond energies for HH. They're giving us the bond energy for ClCl, and they're asking us what is the bond energy for the HCl. So what we can do is we can say the delta H of this formation reaction is equal to the sum of the bonds broken plus the sum of the bonds formed. And we know that that delta H, because it's a formation equation, is the heat of formation of the HCl, which is the 92.3 kilojoules per mole. So all we have to do is plug your heats of, or bond energies in here. You're going to plug this one in, and this is going to be your X. So let's try that. So we have half mole of H single bond. Value for that is 436 kilojoules per mole, and we use the positive value because here we're breaking the bonds, so we use positive values. Here we're forming the bonds, so we're going to use negative values. Okay, took care of that one. Plus half a mole of ClCl single bond. Value for that is positive 242 kilojoules per mole. Again, positive because it's in the reactants. Bonds are broken, and that's endothermic. Took care of that one. And then plus 1 mole of HCl. Use the negative value because it's being formed, so it's exothermic, but we don't know what that value is. That's going to be our X, and we just solve for X. And for some reason I don't have that in my notes, so I'm going to solve for it real quick. So I got X to be 431 kilojoules per mole. And that's our answer.